Right, just a second. If we're looking okay. Okay. All right, how are we doing this morning? Actually, are we ready to go? We have a minute left. What do we do with a whole minute? Post-holiday. But I can't wait for the remaining 40 of you to come flooding in 1 minute. This is going to be, just keep the aisles clear, keep things safe. Anyone do anything fun over the holiday? That fun, eh? College football playoffs, indeed. Fantastic. All right. Okay, let's get started. Oh yeah, sorry. Let's start recording. Thank you. All right. Good morning. Hope you're all doing well. Few course updates. So your first homework is now assigned. Yay! Yay! Exciting! Yay! It's okay. Hey, I will say I really like this homework, but then again, I'm not the one doing it. Okay? It is an opportunity for you all to show how to simulate a system. The thing we did in class on Thursday, right? People were there coding along with me, So we're going to be doing that, okay? It's one of the most important parts, the underrated important parts of doing any kind of control, okay? It's the ability to simulate a system before you control it. That way you can test it in a simulation, and that's what we're doing, okay? There are two main problems, okay? And everyone is doing every part of the problem just because it's important to do this at the beginning of the course to make sure everyone is up to speed on how to simulate systems, okay? Now take heart. I give you what the solution looks like, okay? In fact, if you go onto the Canvas page, you go under Files, you go under Homework, you go under Homework 1, you will not just see just Homework 1, the PDF. You will also see some videos. You're going to be animating your system, okay? How you do that? Well, we're going to be going over that specifically on Thursday, okay? And when is it due? It is due Wednesday, February 4th, okay? Wednesday, February 4th, so you have a little over 2 weeks to do it. I recommend getting started. If you want to get a head start on how to animate systems, there is a MATLAB tutorial, and I'll send along a YouTube link from a previous year where I showed how to animate things, but we'll cover it on Thursday anyway. But there's plenty to do without the animation before Thursday, okay? Again, Wednesday, February 4th, you're going to want to turn that in over the Canvas assignments page. Now, I recommend everyone take a very careful look at the format that I ask for, okay? I ask for a zip file, which has all the files you need. And I'm very specific about formatting on this, okay? And again, it's just because there's so many of you. The only way to grade this in a meaningful way is if everyone's submitting things in a similar format, okay? So we will be deducting points if you do not adhere to the format, okay? Do not underestimate it. It's not hard. It just takes a little bit of time to make sure it is right. So please read the instructions. Further, typically, when people have questions that are very common for these types of problems. So what I found is really helpful is a homework FAQ page, frequently asked questions, all right? So it'll be on Canvas. You should be able to find it on a link on the front page. It's not up yet, but as people have questions, if you have a question yourself, you're like, oh, I have a question about this part. I'll go make sure I go to Dr. Hubicki's office hours, which are listed on the Canvas page, okay? I'll go to his office hours and ask, nay, go and look at the frequently asked questions page. See if I already answer it. Save everyone some time, okay? It might include some hints for people who are having challenges with the assignment, okay? So we try to give you as many resources as possible to be able to complete the assignment, All right? So again, February 4th, Wednesday, 5 p.m. That's when it's due on Canvas. Any questions about that? No. Great. Wonderful to hear. So, with that, okay, let's get started. So today, January 20th, okay, we're going to talk about feedback control. Can't spell today. And linear systems. Okay? So, in class, in our lecture, we coded a simulation of what? What did we code a simulation of last lecture? Anybody? A pendulum, yes. Also rabbits, but also a pendulum. Okay? Now that pendulum, so from our example in last class, we had our pendulum. That was just swinging around. Okay? Where you had some time and you had some angle. Okay? Theta of t over time. And it was doing like this thing, right? To use the technical term. Like this thing. Now, on Thursday, we will actually animate that pendulum. We will create a video of it swinging back and forth. I think that animating things is an underrated skill, specifically for mechanical engineers trying to control mechanical systems, okay? Because sometimes you look at a plot, and that plot will tell you a lot. Sometimes you just want to look at the physical system. And we, as mechanical engineers, doing with mechanical things, can sometimes just look at a thing and say, that doesn't seem right. And it can be a good debugging tool, all right? But we coded up this pendulum right there. It would swing. So in essence, our dynamics of our system in state space form looked like this. That where x of t was our state vector. Anyone remember how many states we had in our state vector for this pendulum? Anybody? I know that lecture is seared into your brain. You were like trying to watch college football. You're like, I can't stop thinking about state vectors. So what was? 2. I see, yes. You're holding up 2 fingers, Marco. Thank you. There were 2 states. They were theta of t and theta dot of t. The angle and the angular velocity, okay? The reason we knew that is because, well, we have theta double dot of t was equal to minus g over L times sine of theta of t. I've written this so many times in my career now. I'm basically a pendulologist, okay? All right? And we said, oh, that's a second order differential equation. We went through Dr. Hubicki's patented formula, came up with 2 different states, okay? And note that when I wrote this, that's a little bar. Just make that flatter, make it look nicer. That there is no control input, okay? U of t, that's our control input. It's not in there. There's no control. There's nothing that's coming in from the outside where we are deciding what it's going to do and adds energy in, okay? So we call it a passive system because it has no active control. Technically speaking, there's also no energy injection, but we'll leave that aside. But it has no active control. It's passive. It's just swinging. It's doing what it's going to do. Okay? A system whose evolution is only dependent on its current state is called an autonomous system. Nick. Now, it's not to be confused with a robot, which might be easy to understand because I always wear the same robot shirt. Okay? It just means that it's only dependent upon itself. There's nothing acting outside that changes how it's moving. What might be such a thing for a pendulum? Well, what if we added a little motor at the hinge that we control? All of a sudden, that system is not only dependent upon itself, it's also dependent upon what you decide to do, okay? And the typical form for that is exactly what I wrote. It's governed by x dot of t is equal to some function of x of t. That's it. And since you basically know everything about how the system is going to move, you can actually say a lot of cool things about it. I could tell you if that system is stable versus unstable. Now, we've not talked much about stability here. If you took controls 1, you might have talked a little bit about stability. Okay? But that's okay, right? Often a goal is if we can put something into an autonomous form, we can analyze it and say a lot of things about it. Okay? But this is a control class. We want to be able to change stuff about it from the outside, right? Who's in charge of the controller? We are. We are. So this is a cool form. We're going to somehow trying to find a way to put this control-based system where we are not autonomous and then turn it into something autonomous. All right? So let me show you a little bit how autonomous systems are actually really handy to work with. Okay? So let's do some examples. Of analyzing an autonomous system. Do a single example. We're going to do something very common. We're going to do the. Sorry, I'm going to zoom out a little bit so I'm not blocking the way there, Nick. Thank you. All right. So we want to analyze the autonomous system. So let's do a spring mass damper. Who here has seen a spring mass damper? I want to see hands. Thank you. Spring mass damper system. Okay? Where you have some kind of wall attached to a spring, which is also attached to a damper. Okay? Now, who knows what a damper is? Yes, I see a lot of you. Okay, I saw you off to the side. What's a damper, sir? Something that slows the rate of movement perfectly. Yeah, perfect, yes. And you still have your hand up. You have a different definition of a damper. You do not. Okay, you're stretching your hand. Okay, so can anyone point to a damper in this room? Yeah, it's up on the door, yes. Ah, that's interesting. Yes, so talk about the acoustic damper, and there's a bunch of acoustic panels in the room. I didn't think of that. They suck energy out of the system, which is exactly what a damper does. It's a little bit different type of damper, but yes. The one that's most consistent with this type of damper I'm drawing right here is on that door. Why is that damper? It's in the upper corner of that door. Why is that damper on that door? What does it do? Yes. It slows how fast the door closes, so it prevents it from slamming, right? So as it compresses, it pushes back and slows it down. Okay? Then of course you have your spring with some stiffness K. You have some damper with some coefficient called C. Then you have some mass here. Mass. and we'll define the stretching of that spring as some S of t. And you're like, Dr. Hubicki, why not X of t? Why not X of t, friends? We've already used it. I probably will reuse it by mistake at some point in these lectures, but, right? So, you have a spring mass damper system. Now, you sum all the forces, you do a free body diagram, you see, you would come up with the fact that the mass times acceleration, so the mass times the acceleration, S of t, or what we would call S double dot of t, is equal to, so let's just say the stretching of this spring, the linear spring, so we'll say it's minus k times S of t. And the beauty of a damper is that instead of fighting position and stretching, it fights rates of change, right? The velocity. The faster it's moving, the more it fights you. So it's actually minus c times S dot of t, right? Okay. Those are our dynamics for a spring mass damper. You've seen them before. Okay. I'm going to put this in state space form. Okay. So we're going to put something in state space form. We have to know how many states there are. Can anyone just look at that and tell me how many states there are going to be? I hear 2. Yeah, I also hear 2 in my brain because that's the right answer. Okay? There are 2 states. Why are there 2 states? Well, if you go through my patented formula, you would go through all of your independent quantities, all of your independent variables here. So you have an S, and you say, what is the highest order derivative? It's 2. What's the lowest order derivative? S of t is, it's a 0th order derivative. That's 0. 2 minus 0. Mathematicians will tell you it is 2. Okay? So there are 2 states. We have 2 states. Okay? Your first state, we start with the lowest order derivative, which is S of t. Then we step up to the next higher order derivative, which is S dot of t. Okay? And then we hit S double dot of t. That is our highest order derivative. So what do? We stop. Stop. We don't include it. That's the process. If you need a refresher of the process, lectures are online. Lecture notes are also almost online. Okay? I have them all saved as PDFs. I just got to upload them, but all the lectures are online. Okay? So we have 2 states, S of t, S dot of t. Now we need to write the derivative. Sorry, let me put a little bar here. At some point, I will ditch the bar, but today is not that day. Why am I putting a bar over the x? It's a vector. Vector. At some point, I will probably ditch it. Okay? So x dot of t, which is the derivative of that vector, because we're trying to put this in state space form, which says that x dot of t is some function of x of t and u of t, but there's not going to be a u of t here. Okay? So the derivative of x dot of t is the derivative of everything inside of x dot of t. Not too hard. So the derivative of s of t is s dot of t. The derivative of s dot of t is s double dot of t. Okay? And we want to write that in terms of our states. Okay? So s dot of t, in terms of our states, is easy. S dot of t is a state. So it is s dot of t. And s double dot of t, as we just said very loudly, is not a state. However, we do have this beautiful equation up here that tells us what s double dot of t is in terms of our states. Great. I'm just going to write it off to the side here, that s double dot of t is equal to 1 is going to be equal to this entire right-hand side divided by m. So it's going to be minus k over m s of t. And minus c over m s dot of t. this little box, starting to crowd my own space here, so I'm going to box that in. So we now know that S double dot of t is equal to all this. That's a state, that's a state. Let's just write this all in here. Okay. This is minus k over m S of t minus c over m S dot of t. Now it's in state space form. Rewriting it just real quickly, S dot of t, and then minus k over m S of t, minus c over m S dot of t. Now this was helpful in our coding. Oh, first off, any questions? Any questions about that? Okay, just same process over. We did it, doing it again. Okay, which is with a different system. Okay, now this was handy for our coding lecture. Why was this handy in our coding lecture? Yes, Christian. Gives us equations to plug into MATLAB, perfectly safe. And the hand gestures were helpful as well. Yeah, they allow us to simulate the system using these first order approximation methods, such as Euler's method, where we say, hey, here's where we're at. Let's take a little step forward, going the slope, take another step forward, going the slope. That's Euler's method. And we were able to give this to ODE 4.5, where ODE 4.5 chose the time steps for us and used a more accurate method. Okay? It was practically helpful in that way. But there's more you can do with this information. Okay? It just so happens that in this system, I see all my state variables here, right, my friends? I see those state variables. They are only multiplied by constants and then added to each other. For any smarty pants in the room, any idea what kind of system I'm referring to here? Rhymes with Schminier? Linear. Oh, yeah, it's linear, right? So it is a linear system. We'll talk about this more formally in a moment, slightly more formally, okay? But this is what we call a linear system. We're not taking the sine of our angle to get the pendulum angle, right? That's nonlinear, okay? We're just taking states, multiplying them by a constant, k over m, c over m, then adding them together. So it's going to be a linear system. So you can do an interesting trick with this system, okay? I'm going to rewrite this ever so slightly, so it's still x dot of t. I'm going to rewrite it as 0 times s of t on the first element, plus 1 times s dot of t in the second element. That's the same. We're all chill with that math. We didn't break any rules. We're all good. And here, I'm going to say this is minus k over m s of t plus negative c over m s dot of t. No mistakes there, right? Here you can very clearly see, here are your states, and here are your coefficients. Okay. So there's a way to rewrite this using matrix math, because this here is a vector, right? Just 2 elements down, 1 column, right? We can actually rewrite this, my friends, as a matrix multiplication, where this is a 2 by 2 matrix, and this here is a 2 by 1 matrix, otherwise known as a vector with 2 rows, a column vector. And right here, we're going to put our states s of t and s dot of t. And in this matrix, this 2 by 2 matrix, 2 rows, 2 columns, I'm going to put 0, 1, minus k over m, minus c over m. And recalling on the left side, it was just s dot of t and s double dot of t, right? Right? It has a 2 by 1 vector right there. Making sense what I've just, okay. So for people who need a refresher on what a matrix multiplication is, if I were to multiply matrices, as we all as cool people know, you don't multiply two matrices together by saying, oh, this element times this element, multiply, we're done. No, that's an element-wise multiplication. This is a matrix multiplication. So if you wanted to do this matrix multiplication, we're just going to, this just reverses the process, to be clear. It's going to undo what I just did. If you were to do this matrix multiplication, the result of a matrix multiplication has very simple rules. One, you can't arbitrarily multiply any two matrices together. These two numbers have to be the same, right? Must be the same. And the result of that matrix multiplication is a 2 by 1 here. That's the result. Okay. The result will be a 2 by 1. Keeping it in blue for fun. Be a 2 by 1. Now, let's go out to the board here. And I recommend just reminding yourselves about how to do a matrix multiplication if you want to do a matrix. So if you want to know what the first row and first column are of your output right here, I like to take, I have what I call my right-hand rule. This is just my way of explaining how to do this, okay? That I take my right hand, I put my fingers on the elements of on the thing on the right. This is the first column. I want the first column here. And I want to know what the first row is. First row, first column. I take this column, and I want to multiply by this row. So I do this. I say ST, S dot of T, boom. I just rotated my hand to the right. Boom. So it's going to be S of T times 0 plus S dot of T times 1. You're probably not taught it this way. You're responsible for knowing matrix multiplications on your own terms. This is my fun way. Okay. So it's going to be 0 times S dot of T plus 1 times S of T. All right. Now I want to know the second row, first column. So first column, here's only one column to deal with. Right hand, and then I want to multiply by the second row. I take it and I rotate it, boom. S of T times minus K over M. S dot of T minus C over M, and I add them. Question? Yeah. Thank you. Okay, question is correct. What's your name, sir? Yes. Thank you very much. I just made a mistake. Thank you. But I got so excited to do my dance. So it's 1 times S dot of T. Okay? And here it's going to be S of T times minus K over M. So minus K over M S of T plus minus C over M times S dot of T. Okay, that's terrible handwriting, but it's the same thing. You see that, right? Okay, that's just me doing matrix multiplication almost in reverse. Okay? So this here is just our derivative of our state vector, right? It's x dot of t. Right here, this is just our state vector itself, right? We would agree with that? And this here is some matrix. I'm going to call it A. Okay? Call it A. And so altogether, this is saying x dot of t is equal to a, which is in no way dependent upon time, you'll notice. It's just a bunch of constants, times x of t. Okay. This is an autonomous system. You would agree with me? Because the evolution, how much our state is changing over time, is only dependent upon our current state and constants, right? Okay. This A is amazing. It can tell you so much about how your system moves, assuming that you can put it in this form, which if it's linear and what we will call time invariant, you can put it in this form. If you have a control input, there's an extra term, which will look familiar to those of you who took controls 1. But this A matrix, you can analyze that A matrix. Who here's heard of an eigenvalue before? Not required for the course. Yeah, many of you. Anyone going to tell me what an eigenvalue is? Who's brave enough to say what an eigenvalue is? No one's that brave. I'm barely that brave. Okay? All right. So suffice it to say, it's sort of a characteristic value. This is honestly, it's one of the hardest things to explain in a way that's like really accessible to an audience, okay? To a general audience. The idea is that if you have some vector and you multiply it by a matrix, it transforms that vector in some way, okay? And so imagine you have your vector, we'll call it x of t, and again, think of, it's a state vector. You can think of it as being a vector in a space. And you multiply it by a, okay? Something's going to happen to that vector. It might grow and go in a different direction. Or it might shrink and go in a different direction. If this vector is pointed in the exact right direction, or one of the exact right directions, it'll actually purely grow or purely shrink, okay? You can play around in MATLAB and just start multiplying vectors by matrices, and you can play around and try to find a vector that when you plot it, it shrinks and just grows, okay? If you find the right vector that only shrinks or grows, the amount that it shrinks or grows is called an eigenvalue. Meaning that if it stays exactly the same, the eigenvalue is what, friends? 1, multiplied by 1. If it grows, it's bigger than 1. If it shrinks, it's less than 1. Okay? So now, that's a very general introduction to eigenvalues, okay? But if you take the eigenvalues of A, and more generally, eigenvalues are this lambda here. Sorry, apologies. I'm screwing up all over the place today. Didn't come in here prepared for linear algebra, apparently. Okay. So if you take your matrix A and multiply it by V, some vector V, this is how much it grows or shrinks. That lambda is your eigenvalues. There can be multiple eigenvalues per matrix. In fact, there are. As many rows as there are in a matrix, there are that many eigenvalues. And it has to be square. All right? That's just your super brief primer of what an eigenvalue is. In MATLAB, you can type EIG, eig. Give me the eigenvalues. Done. If I take the eigenvalues of A, it will tell me if my spring mass damper will come to rest or explode and get bigger and bigger and bigger. It will tell me that. That's what we call stability analysis. Okay? And this applies to something anything even way more complicated than this little two-state system. I could have 1,000 states for a crazy complicated system. If I can put it in that form, and if I get my A matrix, take the eigenvalues, and I'll tell you if it's stable or not. I'll tell you if the system goes back to a nice rest state or if it grows. Okay, how would you know? So for a continuous time system, I'm going to put in this phrase, I'm going to put in here LTI. We haven't said what that is yet, but I'm taking way too long to get there. It stands for linear time invariant. Okay, for a continuous time LTI system, if all eigenvalues have negative real components, because eigenvalues can be complex, they can have imaginary components, then the system will converge to the state vector of zeros. Meaning, if you were to plot your state vector over time, let's say that's your initial state vector, over time it might just, and if you check the eigenvalues and they all are negative real components, zoop, goes down to zero, back to the origin. It might spiral around, it'll go back to the origin. But if any one of them is positive, bad news. It might spiral out. It might just go straight out. Either way, it ain't coming back. Pretty important to know, right? And sure enough, if you compute the eigenvalues for that spring mass damper, if you have a physics-obeying damper that takes energy out of the system, guess what? It's going to be stable, and those eigenvalues will show it to you. Okay? But if you have a magic damper that has a negative damping coefficient, meaning it adds energy, that eigenvalue is going to be positive, and it's going to shoot off. That's pretty valuable, right? To know if your system is going to fall down. Question? Yes? Yeah. Yeah, yes. Of A. Write that. Let's write that out. Of A. Thank you for the clarification. I mean it sincerely. I'm so excited to wave my arms around. I miss words. So, that's pretty cool, right? I don't care if you have 1,000 states in your system. They'll tell you. But this is a controls class. While it's nice to know if this system, and here's an example, by the way. So like, let's say I'm a robot and I'm standing on one foot. Right? Without control, with just the slightest little perturbation, boop, falling over, right? I would need control to stabilize myself. Who gets to decide what that controller should be? We do. Okay? So if we have a way to take a system with control and turn it into this autonomous form, that's awesome. Okay? Any questions so far? Good questions so far. You're finding mistakes, getting clarifications. What more could I want? Other than not making mistakes or not needing clarifications. Okay. Fantastic. All right. So a little bit of definitions. Let's backtrack a little bit. Okay? That system that we created, that spring mass damper, happens to be linear, meaning that the dynamics are just states or control inputs multiplied by constants and added together. Linear systems are awesome. If your system is linear, you can do so many awesome things without a lot of computation. Okay? Also, let's take a look at this A matrix here. You'll see things like spring constants, mass, damping coefficients. You'll see I did not write they are dependent on time. We're assuming they're constant. Okay? Let's assume it's a constant mass. That's not a sandbag that someone stabbed with a knife. okay, and it's drawing and it's losing sand, right? So this system is not dependent upon time. It is invariant with respect to time. We call it time invariant. So let's do two definitions. Linear systems are systems whose derivative with respect to time is only dependent on a linear combination of states x of t and inputs u of t. Okay? And a linear combination, for example, is just so it'll be x dot of t plus b1 times some state x1 of t plus b2 times some state x2 of t plus dot 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 dot. You have as many states as you want. Actually, and then I'll say c1 u1 of t plus c2 u2 of t plus dot 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 dot. Okay? For however many vectors, anyway, so do you get that? That's a linear combination where these are constants. Okay? Okay? And any, yes, question? No. No. Oh, did I? Oh. Thank you, Christian. Frustration is with me, not with you. We're cool. I hope you know that, Christian. We're so cool. How delicately he backed me into my mistake. Like, did you notice that? Oh, I didn't notice that. Thank you. Perfect. Nicely done. All right, that clear? Those are constants, times your states, times your inputs. Those inputs, those could be things like a torque to a motor. Okay? In one of your homeworks, it's going to be the amount of chemotherapy you give to a patient who has a tumor. Okay? All right. So on homework 1, which is due Wednesday, February 4th, 5 p.m. All right. That's a linear system. Okay? So all linear systems, particularly we're going to talk about of ODEs, ordinary differential equations. So let's not talk about your partial differential equations. Okay? All right. All linear systems of ODEs can be written in the form x dot of t, oh, I forgot my bar, x bar dot of t plus A, which is a matrix, times x of t bar, plus B, which is a matrix, times u of t bar. If A and B are not dependent on time, the system is called time invariant. Okay? Question. Then it's not time invariant. So if A and B, not A or B. Okay? So two things I want to point out about time invariance. I'm very clear that A and B, there are these matrices here. They're the things that are not dependent upon time. Because the system is moving, so things are changing with time. My spring is springing. My legs are kicking. They are moving. But the system itself is time invariant. That means things like the masses aren't changing. The spring and damping coefficients aren't changing. No, it's not losing mass. If it was losing mass, then this would be dependent upon time. And thus it wouldn't be time invariant. Fact 2, very important about time invariant. This is an A. All the cool kids spell it invariant, not ENT. We all want to be cool deep down. Maybe that's me projecting on all of you. Okay? But I want to be cool. So it's invariant, not invariant. Note that for an upcoming quiz. Okay? Is it spelled with an A or an E? That's right. Okay. So if a system is linear and time invariant, it has a very important acronym called LTI. Stands for linear and time invariant. Cricket. Is it spelled with an A or with an I? Is invariant spelled with an A at the end or an E at the end? That's right. Marco. Is it spelled with an A at the end or an E at the end? Right. Okay. LTI, linear time invariant. That term is everywhere in controls and systems. In fact, if you just grab a random research paper about control, odds are you'll probably stumble across LTI and be like, ooh, I know what that is. Linear time invariant. So this equation, my friends, x dot of t is equal to a x of t plus b u of t. This is called the state equation for LTI systems. Okay. One little parenthetical I'll point here, just for completionists. This is for continuous time systems. We will mostly be dealing with continuous time systems in this class, meaning that time is a continuum, that you could have time equals 1 second, 1.1 second, 1.1875 seconds, down to all these minuscule floating point values. There are discrete time systems where your system is on a clock. That there is no time in between those two clock cycles, okay? For which the equation is slightly different, for which the eigenvalue stability analysis is slightly different. But you can use a lot of the same tools. It's just like the math changes just a little bit, okay? And in the digital age, that computer there, all your computers there, they run on little clock cycles, right? Clock, 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 clock. They're just so fast you don't notice, okay? So there's a reason discrete time systems exist, but not even just for computers that are on clock cycles. While it is true, my friends, if I may call you my friends, that, let's say I am walking around, okay? Yes, I am in continuous time. We are all in continuous time. We all enjoy being in continuous time, okay? Anyone got any questions about what I mean by continuous time? That time is flowing freely. It's not clap, 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 clap on top on a clock. Okay? So I'm moving around fluidly in time. However, my friends, if I am walking and I am curious as to whether or not I am stable in how I walk, I can rewrite my equations for my dynamics. So I'm now in discrete time, where every time my heel hits the ground, boom, I'm in a new state. Boom, I'm in a new state. And I can write this as a discrete time differential equation and do stability analysis, checking the eigenvalues of the A matrix of my motion. Anyone here take biorobotic locomotion? Anyone, is that now or was that last term, another term? 2 semesters ago, so I'm going to put you on the spot, okay? Do you remember something called like Floquet multipliers, or coming up with the doing the stability of a walking gait by doing a derivative of a map or something? Or yeah, that's what this is. That's what this is, just written differently. Okay? So you can, this is another class that we have in the department. Feel free to check out Dr. Clark's class. It's pretty cool. All right. So you see this, x dot is equal to ax plus bu. You'll see that all the time. Who here took controls 1? Did anyone see that? Controls 1? I'll assume the answer is yes. Okay, I'm sure at some point you saw that. Okay? Now, is this system autonomous? Based on the definition we talked about before. Is it only dependent upon the current state in A? Oh, thank you, Ghost from Beyond. It's not. It's also dependent upon this. Bu of t. Okay? Where u of t are your control inputs. And let's give some of these things names here. Okay? This A is called the state matrix. This B is called the input matrix. Okay? This is the input vector. That's, of course, you all know what this is, friends, right? What's that? State vector. I heard someone whisper it. Thank you. That's the state vector. Okay. And of course, that's the derivative of your state vector. Now, if you took control systems 1, you probably saw there's a second equation. Okay. We won't deal with this right now. But it's y of t is equal to c x of t plus d u of t. This is called the output equation. I just don't want to leave you hanging. For those of you who took controls or know what that is, in case you don't, this here can be either this is called the output, y. It can be the thing that you care about. It can be the thing that you want to make sure goes to a particular position in state space. Or it can be something you measure. Okay? One thing that we have not covered yet is that while it's nice to have a complete measurement of every state in your system, that's not always plausible. Okay? So you can actually use limited sensor information to infer what the state is over time and be smart about it. Okay? It's called an observer. This is actually super important. Okay, you're getting a Dr. Hubicki random tangent. Okay. Okay. So who here has heard of the Apollo program? I hope a few of you. We're actually launching a new lunar program. I think in the next 2 weeks, right? There's going to be a new launch. Well, it's not going to go to the moon, but it's going to go around the moon. Is that what we're doing? Yeah. Pretty crazy. Artemis 2, right? Artemis 2. So we're all back to that. Okay. Now, back in the original Apollo program, back in the 60s, there was a significant problem, which is just knowing where the spacecraft is. Okay? And so the challenge was, how do you use the limited measurements that you had? You have a little gyroscope and a little accelerometer to figure out how you're moving. Okay? So an accelerometer senses acceleration, clearly enough, okay, appropriately enough. You actually have one in your phone. Okay? It senses the acceleration due to gravity, so that's how it knows if it's in portrait or landscape mode. Okay? It's also like if you're in a car. If you were a kid and you were in a car and your parents and you were asleep, and all of a sudden the parents stop the car and you're like, oh, fall forward. You feel that acceleration, right? We can use that acceleration data to be like, oh, I move forward a little bit backward. Okay, this is probably over time how far I went, right? And there's gyroscopes. They sense rotation, right? And those sensors were only so good back in the 60s. And so how do you use that information to say over time, where am I? So Rudy Kalman, who's like a famous mathematician, electrical engineer, came up with a special kind of mathematical filter to take in that state information, come up with a better estimate as to where we're actually at, based upon the measurements that we have. It's called the Kalman filter, K-A-L-M-A-N, right? It's one of the reasons we got to the moon, and it has to do very much to do with control systems and LTI systems. Okay? The exact details of it, not today, but it's important. Okay. So, how are we doing on time? Good. Okay. So this is not an autonomous system, what we're getting to. Because these control inputs, these U of t's, we decide what U of t is. So U of t, let's just for an example, for our spring mass damper, let's just assume it's a force, capital F of t, that you're pulling on or pushing on that block. And we get to decide what that is. We could say, hey, F of t, we want it to be off, or we want it to be on, then off, or we want it to be that, whatever we want. We choose. So much freedom, we can choose anything. Okay? I forgot a little bar for the U right up there, for completionist sake. And I forgot a little bar for the U up there, for completion's sake. Right? Nifty. We get to choose that. However, people who took controls 1 know there's a couple of good choices that you can make as the type of control that you want. Let's just assume we want our position, which we called S of t, to go to 0, and the velocity, S dot of t, go to 0. Okay, just simply, want to go to 0. Whatever that position is, go to 0 and stop. Okay? If this is a stable system, it'll eventually get there. But maybe we want to get there faster. Maybe we want to get there slower. Who knows? That's right. I could learn a thing or two. All right. So, okay. So we can design a controller to drive the system to our desired state. Okay? Thing is, now we also have to change our equations because now we have a force in the mix that wasn't there before. So if we were doing our free body diagram, voila, we have a new force. Right there. Okay. So our control input vector, we have now a force in it. It's got F of t. Okay. If I were to rewrite my state space form, x dot of t, I will speed run the state space form. I'm going to do all the same steps I did before, where it's the same states. So the derivative of your state vector is going to be the derivative of your first state, which is s dot. Then you take the derivative of your second state, which is s dot, and it becomes s double dot. okay, is going to be equal to your first derivative of your first state. S of t is a state. Then we had minus k over m s of t plus minus c over m s dot of t plus, this is actually pretty simple, it's just 1 over m times our force if we worked out the equations. It's that simple. We just add a force pushing to the right. It would show up in the equation like that. Okay? All right. Now, we're going to make what we call a feedback controller. Feedback controller. Meaning, our control input, u of t, is going to be some function, I'll call it g, of our state, x of t. This is our state. We measure it, and what we do is dependent upon where we are. That seems to make sense. We're out all the way over there, let's push us back. We're all the way over there, let's push us forward. There are many ways we can do that. The way we learn in Controls 1 is something called a PD controller. There's a PID controller, but we're going to skip the I for a few just technical reasons. We don't need it, turns out. Okay? Meaning that we want to have a force that's going to be proportional by some constant k. What's the constant k called? We had a name for it. Gain. We talked about that in lecture 1. Some constant multiplied by what we call our error. Now our error is where we want to be, which is at 0, minus where we are, which is at position s of t. You have a d gain, kd, a new gain. Where do we want to be in terms of our velocity? We want it to be 0. So our error is going to be 0 minus where we're at. Our current velocity is s dot of t. Okay? So I can rewrite this as f of t is equal to kp times minus s of t plus kd times minus s dot of t. You'll notice, again, I have here state variables in a state vector, and these are constants, right? Those gains. Who chooses those gains, by the way? We do. But they're constants that we chose. So we could write this. If we pull out the negative sign from both of these, it's going to be minus capital K, which is actually a matrix, times s of t, s dot of t. What's this? Yeah, x. It's our state vector. And what's f of t in terms of, that's u, right? We defined it up here. It's just our control input, u of t. There's only one control input in it, our force. It's u. Question, Cricket. Yes, and what they would specifically look like, my friend, that k would look like this. Kp and kd, it's a row vector. So you can rewrite this as u of t is equal to minus k times x of t. It's called a linear feedback controller. Who here has done a PD controller before? You wrote a fantastic. They're super easy. You multiply your current the thing you want to control. What's that error? By a constant. Then you add the derivative of that times another constant. Proportional derivative PD control. I think I should write out proportional derivative. All right. That's what PD stands for. Linear feedback controller. So that PD controller that you've written out many times, you could write in this way. Okay? Interesting. Turns out this is a super important form for feedback controllers. In fact, let's go back to our LTI state equation, which is x dot is equal to a, of t is equal to a x of t plus b u of t, bar, bar. Look familiar? We've written it like 4 or 5, 20 times now. Get used to it. X dot is equal to ax plus bu. Just because you might not, hopefully maybe I didn't sell it hard enough as to how cool of a form this is. Because something in that form, you know how we did MATLAB simulations using ODE 4.5? ODE 4.5 is great for systems that are nonlinear. You can use it for linear systems. But if your system is linear and time invariant, you can just give MATLAB A and B, and it'll simulate it. You need an initial condition too, Pretty cool, right? Just to show you that it's practical. But again, not autonomous. Not autonomous because it's dependent upon u of t. But my friends, we just said that u of t could be this linear controller, minus k x of t. Super useful form. Why? Well, let's write it again where we substitute in to u of t that minus kx. So it's equal to a x of t plus b times the quantity minus k x of t. Making sense so far? I just shoved that in. That went right there. Now, using the rules of linear algebra, I can just I'll make a slight change. I'll say a x of t is equal to ax of t, and I will take this minus sign and I'll move it out front. It's just a -1 constant times everything, so it's just -1, so I'm going to do a minus. Now, matrix multiplication. You cannot just arbitrarily switch the order of matrix multiplication. You cannot. In case it's been a long time since you did matrix stuff. Can you arbitrarily switch the order of matrix multiplication? Exactly. The answer is no. You in the back. Can you arbitrarily switch the order of matrices in matrix multiplication? No, you can't. There are special rules where you can, but generally you can't. So that means you have to keep this b times k, not k times b. You can't just commute them. Okay. But you can do that, right? And you can simplify this by saying x dot of t is equal to the quantity a minus b times k times x of t. And I forgot a bunch of bars here, so I'm going to put them bars in here. Boom, 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 boom. I just factored out x of t on the right. And it gives me that quantity. This is not wizardry, right? So this here, that's a matrix. Let's call that matrix we'll call it A tilde with a squiggle on top, which is equal to A minus B times k. Which means I can rewrite this equation as x dot of t is equal to a tilde times x of t. Does that look kind of familiar? Is that system autonomous? It is. No longer dependent upon just some u of t, because I said u of t is dependent upon state, and I just substituted back in. Okay? Now, a tilde, of course, is dependent upon k. Who chooses k? We do. But for any choice of k, we'll know what a tilde is. What can a tilde tell us? What did a tell us for the autonomous system? It told us whether it could be stable or not. So in this form, we can choose k's, check the eigenvalues of a tilde, see if it's stable. Even if a wasn't stable before. Just like my example of me standing on my toes, right? I'm not stable without a controller, but if I came up with the right k value under the right scenario, I am stable. Okay? So now we can use all that cool math for autonomous systems with controls. Do we know if our controller is any good? Okay. I'll go you one further. Okay? This choice of k, you could just thumb in the wind, choose it, right? You could just thumb in the wind, choose k's, which are, as we know, as Cricket pointed out, kp and kd. We choose both of those. We can try them out and see if it's stable or not. We just give it a shot. Okay? Or you could just have a method that chooses it for you. Okay? In fact, there are lots of cool methods. There's one where you can say, hey, these are the eigenvalues that I want for my system. I want them all to be negative. So when they have negative real parts, I want them to be -1, -2, -3. Give me the k. MATLAB can do that. Not just MATLAB. There's a method. This method is called pole placement. And just because who here took control? I'm sorry. I'll stop asking that question. People who took controls 1. Not if you heard the word pole. Okay. You can also raise your hand as well. That's good. Yeah, you heard the word pole. Pole is an eigenvalue. When you hear poles, think eigenvalues and controls. Okay? What was the condition for which, again, the people who took controls 1, what was the condition for whether or not a system was stable with a pole? Yeah. All the poles were negative on the real plane, and real negative components. What's the criteria for an eigenvalue being stable? Being negative on the real plane. Poles are eigenvalues, right? So we can do something called pole placement to find k automatically. In fact, in MATLAB, command is called place. Oh, isn't that nice? In the control systems toolbox. There are some conditions. The system has to be what we call controllable. And that means something a little bit intuitive, meaning that, let's just say, there are no actuators on the system. This marker is in the air. While it's in the air, I don't care what kind of k I have. I have no actuators. I have no inputs with which to change where it's going to go. So place ain't going to work. Okay? And there's a mathematical way to check controllability, which we won't have time for today. Future lecture. Okay? Further, this is an optimal control class. We haven't talked about cost functions in almost like a week. I'm getting hives. What was a cost function? What did that mean? Anyone remember? Yes. Well, it tells you what's optimal, right? It tells you what's best. You know, what tastes best at a restaurant, right? Well, you could define something, what controller is best? It could be the controller that gets you back to your 0 as quick as possible. Or it could be a controller that uses as little effort as possible, or a combination thereof. Well, we can write that in math. And guess what? There is a way to take that cost function, take your A matrix and your B matrix, and guess what pops out? A. That's pretty cool, right? Chooses it for you. I say so as well. And that method is called LQR, or the linear quadratic regulator. Okay, we're only at 1 minute left, so regulator. So hope that whets your appetite for how useful this is. All the stuff we went through, we put it into that LTI state equation, otherwise called state space form. I get an A and a B matrix. I know we didn't get the B matrix. Trust me, it's not complicated. We'll practice this on Thursday at our coding lecture. And what if you don't have a linear system? Let's say it's nonlinear. You can temporarily, locally turn it into a linear system and use the same technique. Now I'm done. Thank you all so much. See you on Thursday. Good luck on the homework. Please check it out. Homework FAQ page will be up. I highly recommend checking that when you're doing your homework if you get stuck.